All right, so we're back. We've already done this. Here you can check things are working, buttons are working, everybody's happy. We've got this.
Riley is happy. He has got pay attention now.
Okay, why is wind? It's just got, it doesn't have, oh, the wind from the south is a vector, but the other wind one
Yeah, it's no magnitude.
is no magnitude.
Just blowing south.
Just blowing south.
So the fact that it's blowing, I guess, could maybe argue.
Well, but
The amount.
you don't have the amount.
It's a rough amount of.
Anywhere from here.
So the way that we draw a vector is with a straight line and an arrowhead. So if I have the vector 2, 5, if I go to the point 2, 5, that would be a vector, and we'll write it like this with an x, like the x coordinate on top and the y coordinate underneath. And that is called a column vector. And we define a position vector as a vector that starts at the origin and goes to a specific point. So 2, 5 is just any vector anywhere that goes 2 to the right and 5 up. A position vector 2, 5 starts at the origin and goes 2 to the right and 5 up. So here, we've got the position vector 6, 3. Now you'll see in some textbooks when they draw a vector, they put the arrowhead in the middle of the line. You can put the arrowhead on the end of the line. It doesn't matter.
Is it all right for you to put it at the beginning or at the back?
The beginning would be a little confusing. So in the middle of the line. So in textbooks, you'll also sometimes see vectors written as lowercase bold letters. In the IB course, did you have to underline them?
Yeah,
Or put the arrow in? I like the arrow over top. In fact, in university, I think I did an arrow over half with only half the arrowhead. Okay. So you don't have to actually do another little line. It's just a little bit quicker. So those are just some options for writing vectors and how we write them. Yeah, you can italicize it, which is... Woo! Yeah, take out your calligraphy pen, right? And then you can really...
Is that going to be an example?
There, that looks pretty. That looks like it's bolded and italicized and underlined with an arrowhead over top. Perfect, that's a real impressive vector with all the special features.
Okay, so that counts in the exam when you need calligraphy pen.
Yes. Okay. And we just did this. Okay, so now we can find the magnitude of a vector, another word for it is modulus, by just finding its length. Okay? And so if you had the position vector 6, 3, if we're imagining where that is, 1, 2, 3, 4, 5, 6, 1, 2, 3, if you wanted to find the length of that, well, you know that this length is 6, this length is 3, and so the length will just be a squared plus b squared equals c squared. So we could say that the length of the vector OA is just the square root of 6 squared plus 3 squared, which is the square root of 45. And of course, in a textbook, how would this answer be written? 3 root 5. Properties of vectors. If they have the same length and the same direction, then those vectors are equal. Kind of makes sense. Everything the same, then equal. See? And so it doesn't matter the starting spot. You could have them floating in space, and that's kind of the power of vectors, is we're not necessarily confined to a coordinate system. We can work with them wherever they are. If you multiply a vector by a number, you make it longer or shorter or switch its direction. So we have the vector v there. 2v would be that vector doubled. Negative 3v would be the vector tripled, and notice that the arrowhead changed direction. So multiplying by a negative changes the direction, and multiplying by a number makes it longer or shorter depending on what number you multiply by. In vectors, we have a unit vector. A unit vector has a length of 1. So our standard unit vectors are 1, 0, and 0, 1. And we're going to see some connections between vectors and matrices. And so we start to write, we can write a column vector in terms of the unit vectors. If I wanted to go 6 to the right and 3 up, I could go 6 units to the right and 3 units up. So the I represents 1 unit to the right. The J represents 1 unit up. Of course, you would write this with little arrowheads over top of it. Do you think you'll forget those arrowheads sometimes? Am I going to have notation errors?
It's like plus C.
Yeah, it's like the plus C. So for A, I'll do A and I'll let you do B, C, and D. A would be 3 to the right and 2 up. So we could say that vector A is equal to 3I plus 2J. See how you did? So far, so good? Now, the real nice thing about vectors is that we can work in 3 dimensions. And we can do a whole bunch of math in 3 dimensions that all of the math that we have, our analytic geometry, your y equals mx plus b, your coordinate geometry, that just doesn't work very well once you get to 3 dimensions. It just is hard to work with.
Let's just stick to 2 dimensions.
So we get vectors, and now we can do a lot of that stuff in 3 dimensions. What I want to install one day is a smart board that I can grab like a corner here and pull it out and create a 3-dimensional space in here that I could.
Use your imagination. That's what we're going to do.
Yeah. So you can make that for me.
I will.
So
Make
that
sure you give me a free copy.
like holograms, and I can put stuff in there and spin it around. That'd be very cool.
Yeah, Iron Man.
Yeah,
Iron Man.
I'm almost Iron Man with this thing on. So
It already exists, it just comes to
graphing in 3 dimensions on 2-dimensional paper, how good are you at that?
Bad.
I don't
So-
even want to do it. Real doctor. Actually, I could draw it 3-dimensional.
So what you imagine is you imagine taking an XY on a piece of paper and line that XY piece of paper flat on a table. Can you see here in blue, can you imagine that line on a piece of paper, this line on a desk or something? That's still a 90-degree there. Okay? And then you draw a z-axis straight up and down from there. Okay? So your paper is lying flat, and then your z-axis is coming straight up from there. If I want to draw the vector -9, 3, 4, that would go -9 in the x direction. So that, on my graph, is right here, because that would be your -x. You need to go 3 in your y direction. So here's 3 on my y-axis. So this same distance on this same angle I would measure that way. Okay, now here's the tricky part when graphing this. If this is 4 up in your z direction, this same distance right here has to be brought over here to that point. Does that make sense?
Sure.
And then we've got the vector v starting at our origin to that space out there. Now, here's the formula for that length of v in 3 dimensions.
Let me guess, in 4 dimensions, it's v1 squared plus v2 squared plus v3 squared plus v4.
Yep.
Oh, cool.
It's just a Peter square and V4. Yeah.
All that's happening, okay? All that's happening to figure this out. Can you see that if this length here is 9 and this length is 3, that this red length here would be the square root of 9 squared plus 3 squared.
I see what's happening, yeah.
Okay?
The other thing's
And there's another right angle here. And so you could do, to find the black length, I could do a squared plus b squared equals c squared. Well, this length is 4. So I would get 4 squared plus all of this squared. But what happens when I square all of that? It just becomes the 3 of them together. So the formula, which looks like, ooh, it's kind of the same, but why does it work? Well, now we can see why it works, because it's just a squared plus b squared equals c squared done twice.
That's so cool. You know, once you actually draw the second triangle like that, I can actually visualize it.
So now you can see what's happening.
Yeah.
Nice.
You're doing a great job.
Whew.
Stay alive.
So if we want to find the length of this, the length of vector v would be 81 plus 9 plus 16 square root of 106. Does that simplify nicely?
No, negative.
Probably does.
No, it does not.
No, it's 2 times 53, and 53 does not.
53 is a prime number.
Doesn't help us out very good. So there we go. That's the magnitude of the vector v. So there are 3 for you to try.
What do you want us to do with this?
I want you to find the length of all 3 of those vectors, or find the magnitude.
I got the concept, so I can do the rest of it.
5, root 75, and 7, which I find the last one very fascinating because now we have an a squared plus b squared plus c squared that works out to a nice number.
That's cool. What's the form? Is there a formula that allows you to do that? Oh wait, so the other 2 numbers, 6 and 3,
Add, multiply that. 6. I don't know if that's.
No, well, you have to play around with it, but it does open up a next set. Okay, some of you are already working on the next one, which is great.
wait, you tell me, Randy. How do you figure this out? You square both sides nicely. Yes.
All right, how did you do?
Finish it. Is it plus or minus?
It is plus or minus. Yeah. Should have the values in the question, right?
So much notation.
Mm-hmm. You ready for new notation?
Yes, please.
Okay. Unit vector. So we can highlight that so that's prettily highlighted in your notes.
Can I borrow the green after you're done?
Yes. So the notation for any vector is you put a little hat over top of it. That will be your unit vector in the same direction as the vector u. So we have here our 6, -3, 2. And we want to find the unit vector. First of all, wow, that's still green. First of all, we can find the length of u, because it'll be the square root of 36 plus 9 plus 4, which we already figured out was 7. And so if we want to make our unit vector, we would need to take that length of 7 and divide it by 7. So one way that we could write our answer is divide each of them by 7. So this would be one way to write our answer. I personally like using column vectors as opposed to using the unit vectors because this is a lot going on. My favorite way to write this answer would be like this. I have my original one, 6, -3, 2. And I put a 1/7 in front. I don't have to what? Oh, that would be a third way. If you wanted to, you could write them. You don't have to put it in. In fact, I like keeping that. I like keeping that fraction out in front because any kind of math you need to do with your vector, you can do that and then deal with your fraction at the end. All right, so find your unit vectors for each of these.
Can you say point loss?
All right, there's the first one.
Okay, I was wrong. Sorry. The 1 over square root is 69. What's in the head closer to me? Square root 61. Yeah, there you go.
There it is.
1 and 9 looks almost exactly the same. What?
Oh, that's another one.
Those are top. There's another on the other side.
Yep, one more to try. But now you're trying to, now that you found unit vectors, can you find one that is in a different length in the same direction?
Give us a moment to actually look at how you do it. Someone tried trading me an iPhone 10 for this.
So first of all, I found my unit vector. So the length is root 38, and my unit vector would be 1 over root 38 of the vector that I had to begin with. That has a length of 1. So a vector with a length of root 7, I could just take my unit vector and multiply it by root 7, and then it would have a length of root 7. It's not too bad.